Hello, everyone. Welcome back to the channel. If you've been watching my podcast for a while, you know that I'm interested in the study of human evolution, including understanding some of our closest relatives. In an early episode, I talked with Greg Forth, who studied Homo floresiensis, also known on the internet as the Hobbit. It is a close relative of humans that was discovered in a cave on Flores in Indonesia in 2003. The discovery of the Hobbit caused waves across anthropology because it suggested that potential human ancestors, or I should say relatives of us, existed much later in history than we initially expected and may have survived in places like remote islands up until about 50,000 years ago. The disappearance of Homo floresiensis, maybe you could call it the extinction, was kind of a mystery. Was it caused by the arrival of humans, or was it caused by maybe other reasons or some combination? A new study has come out that has shed light on that question and suggests that maybe climate had something to do with the disappearance of the Hobbit and maybe could help explain the extinction of other species as well. So, to explore that, I'm bringing on co-author Nick Scroxton is here to discuss that with me. Hello, Nick. Welcome to the channel.
Hi there. It's great to be here with you.
Nick, you are one of the co-authors on this study, and you were able to reconstruct precipitation patterns on Flores over the last, I think, something like 80 to 40,000 years ago. So I want to first step back and think about the big picture here when we're looking at this study. The Hobbit, Homo floresiensis, existed on this island going back quite a ways. And first I want to explore, how would climate have affected the development and possible extinction of this species? Why in a place, I mean, it seems like Flores is a pretty wet, tropical, lush environment, and they weren't dependent on agriculture, because in the literature you kind of see archaeologists kind of want to stray. They don't want to, focus so much on environmental determinism. And part of the reason I think this study is so interesting, because it's kind of expanding, this environmentally driven idea to another species of human, essentially. And like I said, they didn't do agriculture. So why would precipitation changes affect Homo floresiensis?
So that's a great first question. So there are several different aspects of the Hobbits' existence. So there's the environment that they would have been in, or that they would have been best adapted for, and also kind of the similar thing for whatever their primary prey would have been, or secondary different types of prey. So Flores is certainly in the present day a really kind of lush tropical island, but because it's located in the Indonesian archipelago, this would have been a dramatically different place during the ice ages. So the Indonesian archipelago has a lot of shallow seas, the Sunda Shelf, the Sahel Shelf. There would have been a lot more land around here. And so not directly next to Flores, but in the region, in the source regions of the rainfall. And so this means that we are able to have very dramatically different conditions in the past, in the glacial versus the present. So it's potentially quite large shifts in rainfall. A purely tropical island with no large continental shelf near it would have relatively minor shifts. This probably had quite large ones. In general, I think it's to do with the vegetation. Currently, the area is, well, where it's not been cleared for rice paddies, the area is quite heavily wooded, forested, whereas we've got reason to believe that there would have been a lot more grass in the past. So the transitions between what's known as C3 vegetation and C4 vegetation. So we've got using the different biological photosynthetic pathways. And so grasses tend to be C4. The trees tend to be C3, with exceptions in both cases. And so we can look at some of their prey, primarily the pygmy elephant stegodon. And we have reason to believe that these elephants would have been primarily C4 grazers.
Okay. See, this is part of the study that I found interesting, was that not only do you see Homo floresiensis go extinct, I think you also see the disappearance of Stegodon florensis insularis.
Yep.
I believe that was really interesting to me, that you're seeing large mammals on the island seem to all go extinct at the same time. And so I guess that then raises another question here, was about just the Hobbit itself. It was, you're implying it mainly ate meat, so it wasn't eating vegetation like, similar to like gorillas in Africa. They're mainly herbivorous. Do they have evidence of like how these hobbits hunted, or what their dominant prey was, or any kind of background on that?
Yeah, so I believe we have cut marks on stegodon bones. So we know that they were hunting those. The cut marks, I believe, also are primarily on the juveniles. So
Mm.
we don't have as much stronger evidence they were hunting the adults. They're probably hunting the juveniles, which makes sense. These hobbits are only a meter tall, and they weren't particularly big. Having said that, it's just as likely that there were also kind of giant rats on the island. They could have been eating those as well. We believe the stegodon was a significant food source, but it might not have been their primary.
Okay. And for, another background piece here, the stegodon is a proboscidean, so it's a relative of mammoths or elephants.
It is, yes, distant.
A
I
distant
can't remember the exact. Again, that's one of the kind of the archaeologists will be able to tell you exactly where on the lineage it fits. But yes,
Okay.
approximately.
Yeah,
to the first order.
Flores has a lot of very strange animals. Like, I've heard about this giant land rat. I think Komodo dragons are from near there, or are they on Flores as well?
So they would have been.
They would have been as
So
well.
the main habitats of the Komodo dragons, natural habitats of the Komodo dragons, are actually two small islands, Komodo and Rinca, which are just off the western tip of Flores. I believe there are still some small populations on Flores themselves.
Yeah, that's fascinating. That it seems like Flores was a hub for a lot of, strange evolution going on in the late Pleistocene. And so if the Hobbit was eating stegodon, that suggests they had pretty sophisticated tools, like projectile points or something like that, for eating these. And you're saying they mainly targeted the small versions, or the younger stegodons. So how big were these um stegodons?
That's a good question.
Yeah, I know you're not the archaeologist or paleontologist, but I just kind of, for the background, I'm trying to picture
Yeah.
the scene here.
How big was a stegodon? To quickly look this up for you. 1.8 meters tall. So kind of human sized, I guess, in terms of height. So, twice as big as the hobbits, the fully grown adults. So
Wow. So if they're hunting those, it seems like they have tools at least, or some way to corral them and get them into traps or something like this. And
something like that. Yeah, it's quite interesting to think about their abilities versus especially their cranial size. Is certainly kind of a fascinating evolutionary question, that they had a relatively small brain, but seemed to have quite advanced cognitive skills and tool use.
Now, your study now was mainly focused on the paleoclimate of Flores, and you used stalagmites to reconstruct this climate. And I know that your part of the project was mainly focused on that. And I kind of want to understand exactly how that was reconstructed, because I have a better picture, and hopefully the listener does, that we have an island here in the late Pleistocene. We're talking 60 to 70,000 years ago, plus or minus 10, 20,000 years. The island has very large animals on there that are fairly unique, and at least the stegodon is probably primarily eating vegetation, and then vegetation forms the basis for the ecosystem out there, including the Hobbit and what the Hobbit eats. So on Flores, you found a stalagmite in your team, and most people just have no familiarity with how paleoclimate is even reconstructed. Maybe not, they might not even know what stalagmites are. So let's get into the details of exactly how you reconstructed this climate. Maybe let's start with, you worked with, first of all, what is a stalagmite and why do they form in caves?
Yeah, so stalagmites are a fantastic paleoclimate tool, in my biased opinion, probably the best one. So they are secondary mineral deposits formed of calcium carbonate, usually calcite, sometimes aragonite. And so water, as it comes down from the sky, goes into the soil, picks up carbon dioxide from respiration, which then dissolves the limestone host rock. When that water kind of percolates down through the rock and enters a cave, the cave has a lower carbon dioxide concentration atmosphere than the soil. And so the carbon dioxide degasses and the calcite is reprecipitated. And so that can be on the floor as a stalagmite, on the ceiling as a stalactite, and the various different drapes, flowstones, all kinds of different formations. And so because this happens very gradually, very slowly, through time with stalagmites, you get this building up a layer after layer of calcite over hundreds to thousands to tens of thousands of years. And so the chemical so because each layer is deposited successively, you've got the oldest at the bottom, the youngest at the top. And kind of like any paleoclimate archive, you can then extract that and measure the chemical composition of that stalagmite up through the layers. So we have stalagmites in Flores we have a continuous record now that's all very close to continuous, that stretches from the present day back 92,000 years over the course of 7 or 8 long stalagmites, and then about 20 shorter pieces here and there that help duplicate this record. So we've been publishing those gradually over the course of the last couple of decades. So the cave was discovered by our team, or at least it was the full extent of the cave was discovered by our team, I believe 2006, I want to say. So Liang Loa is just about 800 meters away from Liang Bua in the same river valley, just a bit upstream. Liang Bua, I believe, means the misty cave or the breathing cave, because a fine mist emerges from it in summer, indicating that there's water inside. And so the locals believe that this cave was about 100 meters deep, and kind of because that's how it's actually fairly easy to walk through that 100 meters. And after that, there's a boulder choke. And it was our team that were the first to kind of, with modern equipment and lights, to scale that boulder choke, realized that the cave then went beyond that, back down the other side, through a sump. So there's a gap you have to walk through to get into this cave, where it's about that much gap between the ceiling and the surface of the water. So you're kind of wading through about 60, 70 meters of water, neck deep water, to get in. And then there's another climb over the top. And then you have to crawl through a very thick mud, army crawl style. And then once you're through about 200, 300 meters cave, it opens up and it's this magnificent, beautiful cave inside. We've explored about 1.6 kilometers of cave. It's exquisitely decorated. There is a lot of mud, lots of different sections of different styles of cave. And we've found various stalagmites in that cave that have kind of helped us piece together this 92,000 year record. And so the most recent paper that we've got, which is this one, is this stalagmite called LR09K2, which I just refer to it as K2. And it covers 92 through to 47,000 years. That's the perfect stalagmite kind of length to cover this Hobbit interval, because we believe that the dating on the sediment in Liang Bua suggests that the Hobbit was in this cave was in Lianbua between about 100 and 60,000.
Okay, just to clarify here, so the Hobbit skeletons were found in a cave, and you're also finding the stalagmites. Were the Hobbits found in this cave with the stalagmite reconstruction?
No Hobbit bones have been found in Lianglua. The opening, they probably went inside the opening passage, but without, they had no access to kind of external light sources. So there's no reason to believe that they would have ever have gone inside, or at least gone inside and been able to get out.
Okay. And how far away is the stalagmite from where the fossils were found for the Hobbit?
So the cave entrance is only about a few hundred meters upstream, 800 meters upstream, and then the cave goes another further kilometer. So we're really only, I'd say, less than 2 kilometers from stalagmite site to Hobbit site, which is nothing in paleoclimate world.
Okay. Whoa. That's cool. All right. So we're really close by where most of the fossils were found. And now when you take the stalagmite, you said that it forms layers. Why does it form layers as it's it's drip water, I'm assuming, coming from the cave through the ground. And why is it forming layers? What causes that?
So it doesn't necessarily have to form distinct layers. So you can get thousands of years where you're just forming just single blocks of beautiful calcite. We kind of end up referring to them as layers far more than they are necessarily visible. There are plenty of stalagmites out there that have gorgeous layering, which can be caused by slight seasonal variations in the material that's being flushed through into the cave, humic acids, dirt sometimes. So you can get annual layering, you can get event-based layering, you can get all kinds of different things that are different sections of the stalagmite that are slightly different colors or different mineralogies. Yeah, be good if you need a. Did I send you a good photo of the stalagmite? I did.
Yeah. I'll
because
pull up
the stalagmite itself is beautiful on the inside. It's really stunning.
Yeah, I'll definitely have that up on the screen. So you're not counting the layers to get the ages. You're using radiometric dating. So what kind of isotopes are you using to date this? And how many dates did you get, if you don't remember exactly, like roughly for that time interval?
So stalagmites, this is the reason why stalagmites are absolutely brilliant as a paleoclimate archive, is because they are so precisely dated. So we use uranium thorium dating. So it's disequilibrium dating. So it relies on the idea that uranium is soluble in water and thorium is insoluble, which means that as the water because all of the material is being transported by water to the stalagmite surface, in theory, at time zero on the stalagmite top, there is no thorium and some uranium. And so because you effectively have zero daughter at the time of formation, you're able to have a very, very precise clock. It doesn't actually work like that. There is external dust and windblown sources of dust, which means that you have to measure the different thorium ratios and different uranium ratios in order to piece that together and correct for that small amount of dust. But in general, we're able to get errors that are less than 1%, often down to 0.25%. So that's the big draw of stalagmites as a paleoclimate archive, is going to be how well you can date things. We can tell when things happened very precisely. As for the number of ages, I had to guess that we've got somewhere around 30, I believe. So we're looking at, let me see, I can bring up the 32.
32 dates.
Precision. 32 dates over 45,000 years. So we're dating once every 1,500 years. And that is a real kind of testament to the daters in the team. They did a great job producing these kind of chronologies.
How long is the stalagmite, like in centimeters or meters?
K2 is about 2 meters tall.
2 meters. Wow.
I believe it's a long one. It's a big one. Yeah.
That's a big drip.
That is, yeah. I want to say it's 2 meters. Yeah. Roughly, it's definitely more than a meter. Maybe 1.5 to 2 meters. It's a tall one. And it's 45,000 years long. So you can imagine the drip. The growth rate is reasonably slow.
Cool. And so 32 dates over, let's say 2 meters. I mean, that's a lot of dates because I work with sediment cores to do paleoclimate reconstructions.
Yeah.
And I mean, that would be unheard of to have that many dates over that short of an interval. So I would say this is a fairly well dated record. And as you've mentioned, that's the strength of using these as paleoclimate archives. And so explain to me, you said the daughter product. So the older layers have more of the decayed daughter product, and then the younger layers have, systematically less. So then
Yes.
the more daughter products from the decay of the uranium into thorium, right,
Yeah.
is proportional to the age. Just for the listener out there, that's kind of how that's how radiometric dating works. It's based on decay rates over time of some sort of radioactive element into a daughter product, and then it's captured in the mineralogy of the archive that you're analyzing. It's just not layer counting and like tree rings, let's say. You actually have hard chronological control that's independent of the actual layering.
Indeed. Yes. Yeah. And in fact, stalagmites are being used as the kind of one of the independent controls on layer counted archives. So such as the ice cores, you end up using the stalagmites just to make sure that you're not drifting off in one direction.
Oh, okay. So you have it dated, and then you're analyzing small bits and pieces of the stalagmite going from older to younger. Now what kind of proxies do you use? Let's start with, I have looked at your paper. Let's start with the isotopes, and then I'll talk about the elements like magnesium and calcium. So what isotopes did you measure in the stalagmite, and what do they tell you about the environment at that time?
Yep. So the classic stalagmite paleoclimate record is generally oxygen isotopes, so delta 18O, measuring the relationship between oxygen 16 and oxygen 18, the stalagmite calcite. They're stable isotopes. There's no radioactive decay going on. And so that ratio changes. Generally, that ratio changes above the cave in the atmospheric system. Different processes in the atmosphere fractionate oxygen isotopes differently. And in particular, convection seems to be a very strong fractionator. So if you are in a part of the world that has a lot of convective activity, so the monsoons, so Flores, you can get very strong fractionation occurring in the cloud cells, just as moisture is recycled up and down inside these convective cells. And so that sets an oxygen isotope ratio, which is then captured in the stalagmite. And it turns out, in general, there's a good relationship between the amount of convection and the strength of the monsoons, and usually a linear relationship with rainfall, such as the traditional view of oxygen isotopes, of tropical oxygen isotopes in stalagmites, is that as the more rain, the more negative the oxygen isotope ratio.
Okay. And then that translates to wetter, basically.
Yeah.
Yeah, wetter versus drier.
Wetter versus drier. It's not, that's the idealized system. There are complicating factors that normally we can't quantify that. And for however good stalagmites are, the x-axis are a bit more hand-wavy with the y-axis.
Okay. So you're
if that
saying
makes sense.
the
We don't
dating
quite
is
know the dating is brilliant. We know when things happened. As to what happened, we're often a bit more cautious. But approximately wetter, drier is generally how we interpret the oxygen isotopes. We do have the carbon isotopes as well. They're not really talked about that much in this paper. In general, they are, if I remember rightly, they're reasonably correlated in the K2 record. And the carbon isotopes, which is carbon-12 and carbon-13, again, the stable isotopes, they're generally set by the vegetation in the soil. And so the more respiration in the soil, the more vigorous the respiration rates and the more vigorous the tree growth, essentially, the more negative that gets. And that just tends to be set by a combination of temperature and precipitation. And if you're in the tropics where temperature doesn't change much, and if your CO2 isn't changing much, changing very slowly, it kind of just lends support that your oxygen is roughly wetter, drier.
interesting. I'm trying to picture this. I'm going to synthesize this for people listening. So you have a cave that's creating stalagmites. The stalagmites are forming because there's drips of water in the cave that when they emerge in the actual cave, they degas, changes the pH in the water that causes this calcium carbonate mineral, which is the elements are dissolved in the water and they actually form at the site of the drip and they form over time, making these layers in sometimes they can be a meter or two. And so the water, though, itself is being derived from precipitation that is falling above the cave, entering the soils into the groundwater, making its way through the geology, which would be karstic or limestone, because we're having caves being formed, and which is through dissolution. The caves are essentially chemically weathered caverns within this bedrock because natural precipitation is a little bit acidic, so it creates these caverns underground, and therefore
And
yeah, and the
and it gets more acidic with the soil.
sorry.
So natural precipitation is slightly acidic because you've got somewhere between 200 and 400 ppm carbon dioxide. So it's carbonic acid. And then in the soil, you can get thousands up to 10,000 ppm carbon dioxide. So yeah, the soil is
Okay.
one of the big ones in
Oh,
terms of
okay.
where the acid comes from.
Oh, that's good to know. So then you pick up more acidity in the soil as it moves through. Now, when we think about the precipitation above falling onto the cave, you mentioned that you're getting fractionation of these stable isotopes of oxygen. So you have the O18 and O16. Can you maybe explain, generally speaking, when you get wetter conditions, why does it change the isotopes? Like, what's the direction? You get more of the lighter isotopes when it's wet, or do you get more of the heavy ones and vice versa?
So it's more of the lighter, I think. Sorry,
Yeah.
I'm 95% sure on that. I always go, hang on, which way round is it? More negative, and it's 18/16.
It's 18 over
Yeah,
16. Okay.
I think, or is it 16/18? You live with this so often, and then you're actually asked, hang on, which is wetter and which is drier again? It's
Yeah, you
more
can,
negative delta 18. No, different keyboard.
because the ratio itself is 18 over 16.
It's
When you,
18/16. So when it's wetter, you get more 16. So it gets more
so
negative.
in the cave, yeah, the
Yeah,
direction
sorry.
is more negative is wetter in the actual isotopes in the cave
Yeah.
record, and
So
then more
So what
positive is drier.
basically happens is that in the atmosphere, so the water is evaporated from the surface of the ocean, goes up into the atmosphere, has a certain set isotopic value there. Then, depending on how much is cycled and how much rains out, 18 tends to rain out preferentially to 16.
Okay.
And so either when you have only a small amount of rain, there's a lot of 18 in it, and the 16 stays in the atmosphere. Or if you're working, or if you can think about it through space, then the earliest rain is the closest rain is 16, and the closest rain is 18. You get much more 18 out first, and then the more fractionation you get, the 18 keeps dropping out, and so the rain, when you have lots of rain, that's when the 16 has to drop out because you've run out of 18.
That makes sense. And this is like, I don't remember the name of that. There's a technical term for that where it's a kind of the evolution of the precipitation.
Rayleigh
Me
fractionation.
Yeah. Okay. Oh, yeah. That's what it is. And
Yeah.
so that essentially is the mechanism by which the isotope ratios are then sensitive to overall climate on the island. And I also noticed, we don't have to necessarily get into the details here, but in your paper, you do account for the fact that oxygen isotopes, the starting point of the oxygen isotope in the water itself is always the ocean, especially in these island environments. I mean, in other really interior continental areas, maybe this is not the case, but
Yeah.
it starts with the ocean. But the ocean water itself, the isotopes have changed through time because we're talking back in the glacial period when a lot of ice was locked up, a lot of water was locked up as glaciers on land. So the whole starting point of the water in the ocean was different. And in your paper, you do mention that you account for the changes in the ocean water oxygen isotopes, the starting point of the water. And we're able to then, calibrate your paleoclimate record. So you're not just simply recording the change in the ocean water.
Yes. So a kind of a similar effect happens that in terms of the precipitation and then eventually snowfall in the northern latitudes, you tend to get a lot more 16.0 in the colder weather and in the snow and then the buildup of ice because it's further away from the precipitation source, which is the ocean. And on a year-to-year timescale, that doesn't matter because the snow then just melts and runs back into the rivers. But over these tens of thousands of years, when you've got the ice sheets growing, you get more and more ice just building up, and that becomes a store of 16. And so the oceans gradually get richer in delta 18.0 as you get more ice. So we do have to correct for that. The correction overall is at most ends up being 1 per mil between kind of modern and last glacial maximum. So you're looking at a 0.1 per mil per 10 meters of sea level change. And so we're able to correct for that. So that's an overall correction of 1.1 at the most. Back here, 60, 80,000 years ago, obviously the correction's only going to be half that, or perhaps even slightly less. And that's in comparison to the isotopes in the stalagmite themselves are changing between about -7 and -4. So we've got a 3 per mil range. So we don't have to correct. You could see most of the signal there if we didn't correct because the signal in the rain is 3 times larger than the signal coming from the ice. But we do correct. We can correct, so we do correct.
Okay, that's good. You're trying to cover all your bases there and
Yeah.
isolate the signal. Now, in addition to the isotopes, you also measured the elements in the carbonates, including magnesium and calcium, and you ratioed that. Can you tell us what that means?
So this is a slightly newer technique, although it's really been around now for decades. So it's mainstream and is almost becoming preferential, actually, this idea of trace elements as a way as a proxy for much more the local hydrology. So very much the rainfall in right above the cave and how the water acts as it goes through the cave system. So in limestone, there is both magnesium and calcium. They are 2 elements with a very similar charge, a very similar diameter. So limestone will always have a certain amount of magnesium in it as well as calcium. So, but there are slight differences and therefore they have different fractionation factors. And this means that when calcite precipitates, it prefers to precipitate calcium. So it will always take slightly more. Whatever your initial mix is of calcium and magnesium, it prefers to take slightly more calcite. And then so that means that when you precipitate calcite, you get quite calcite rich at the start, and then you get slightly more magnesium rich at the end. So it's all about where along the system from dissolution down to stalagmite does the calcite occur. So when it's drier, the water takes longer to get through the system and encounters more pockets of air in the cave, and it spends more time on the stalactite surface. So you've got a stalactite usually hanging above the stalagmite, and there's going to be precipitation on that as well. And so the drier the conditions, the more precipitation occurs before the water gets to the stalagmite. So there's more precipitation in the voids just above the cave. There's more precipitation on the stalagmite, on the roof, and more on the stalactite. And so that means that the stalagmite, the calcite that forms on the stalagmite, ends up with more magnesium. So therefore, we've got another wetter, drier situation whereby, in general, wetter conditions is less magnesium. So the magnesium calcium ratio goes down.
Okay. So then magnesium calcium ratio goes down with wetter, magnesium calcium comes up with drier. And then you can then compare that directly with the oxygen isotopes measured from the same layer. And you have, two lines of evidence for your interpretation of the climate in this record.
This is the really neat trick about what we did here. And this is the bit that's this would be exciting to stalagmite people. Well, I hope, even if we didn't have the Hobbit stories. But what we've done here is actually really quite exciting. So we've measured the oxygen and the magnesium on the same powders. So we've got paired measurements. Often people tend to do magnesium through laser ablation, which you're working on a slightly different sampling rate, and so you can't quite match things up. But we have paired measurements. And so what we have is the magnesium calcium tells us about the local hydrology, wetter or drier, pretty much as our year-round signal. And the oxygen isotopes is telling us something about the summer monsoon rainfall. So then essentially you've got, to get a full delta 80 what we've managed to do is separate out the seasonality here. We've been able to reconstruct annual, winter, and summer rainfall. So you need to know four different things. So you need to know the winter rainfall and the winter delta 80 and the summer rainfall and the summer delta 80 in order to do a mass balance to get mean annual rainfall. Right, so you've got 5 variables there. And so normally when you only measure delta 80 you've kind of been able to, the delta 80 of the summer. And this is why we don't normally do reconstructions. That's why we don't turn these into millimeters on our graphs. With the magnesium calcium, we can then figure out the mean annual rainfall approximately. So we've got an independent assessment of mean annual rainfall. And then by a stroke of luck, the delta 80 of the winter rainfall in Flores is very homogeneous. It's basically the same. And that cancels out 1 degree of freedom in our equation. So normally when you can't tell the difference in a stalagmite between a change in change in the amount of rainfall or a slight change in the delta 80 due to other processes or due to a change in winter precipitation.
Mm-hmm.
In the tropics, we tend to ignore it because we just go, 80% is monsoon, and therefore the majority of the signal is summer, and therefore we're reconstructing monsoon rainfall. But because the winter rainfall is so remarkably homogeneous in Flores, we cut out 1 degree of freedom, and that means that we can use the delta 80 and the magnesium calcium together to calculate winter rainfall, summer rainfall, and mean annual rainfall. And basically that hasn't been done, and that's the new technique that was able for us to reconstruct all 3 of those, and therefore we can start looking at seasonality. We're not just saying wetter, drier monsoons. We're not just saying kind of wetter, drier overall. We're saying we've got winter, we've got summer, we've got mean annual.
That was good. And I know how complicated it can get. And it's hard. If you're listening to this, when you have these isotope signals, sometimes they're strongly affected by when the precipitation falls rather than just total annual. And because summer precip versus winter precip can have different signals. And so sometimes you may see what seems to be like a wet phase, but it's because it just happens that there might have been more winter snowfall that was very strongly negative and it's weighted towards that in the signal. And so what Nick is trying to do is explain how you can take all these, I like how you call them degrees of freedom, and try to reduce it down.
Essentially, we were able to get all 3. We got
Okay.
winter, summer, and mean annual.
Okay. Delta 18 reflects a mixture of low O18 convection from summer monsoon rain, and high delta 18 is winter trade wind rain. So this is that idea that if you see an oxygen isotope signal, you can't just say simply more rain, simply less rain. It also has to do with when the rain fell and came, or the precipitation. So if you have your figure open, now we have the proxies together. And what's the broad synthesis you're seeing from the beginning of the record from 91,000 years to 41,000 years? What are the trends you're seeing in the climate?
Yeah, so we're kind of seeing 3 distinct phases in the climate. So our first phase, which is kind of mostly marine isotope stage B, seems to be wet all year round. Kind of, it's a wet summer, reasonably wet winter, kind of equivalent to, and we also translated this into latitude to kind of help people understand roughly the equivalent latitudes climate. So at the moment, Flores is about 8.5 degrees south. During Isotope stage 5, this kind of wet summer, wet winter would have been something a lot similar to, even closer to the equator, say 5 degrees. Similar in climate to what we might see in Sulawesi or Borneo in the modern. We then had a drying in winter rainfall such that, summer declined a bit, winter declined a lot. So we have this second phase. So we then enter a second phase between about 77,000 and 61,000 years ago. So the summers get a little bit drier, but the winters seem to get a lot drier. So we get this very seasonal climate at this point, and that is far more akin to something we might see slightly further south in northern Australia. So there's very much the vast majority of the rainfall is during the summer, during the monsoons. And then we get a third phase where the summers also kind of get drier from around 61,000 years onwards. And so there we've got a dry summer, dry winter, and the climate's a bit more similar to what we might see nowadays in, say, southern Queensland.
Okay. And what was the time period for that last one?
61,000 years onwards.
Okay, till the end of the record.
The end of the record is about 48,000 years. Yeah.
And so then that would be considered the most dry period in the Reconstruction overall, right?
Yes, it was possibly driest between about 60 and 57, if you wanted to narrow it down to the real extremes of the records. If you're breaking it down into the three broad areas, then yeah, it's about 61 to the end. If you're going for the really dry bit, that would be around 57.
See, this is where it gets interesting now, because you found this really dry bit here, and then I'm sure one of you or talking to your colleagues realized that if you pulled up the fossil dates from Floresiensis, the Hobbit, and other fossils like the mini elephant, the stegodon, they seem to all date to just before this dry interval, correct? And after that interval, there are very few dates of the Hobbit.
Yes, eventually that's what we found. So if you just take the Liang Bua deposit dates themselves, the bones are fairly spread out throughout this interval from around 120 up until around 50,000 years. And I think because sediments are a lot harder to date, there's a few luminescence dates. There's a very dirty flowstone in there. There's the fairly large tephra, which I believe we've dated 50,000. So and the dates are a bit loose within those. There's roughly just kind of a straight line that runs through if you just use the dates as they are from Liang Bua. But what was quite remarkable is that when you look at the delta 18O of the enamel of the stegodon teeth, the baby stegodon teeth, so that similar process, the stegodon are getting their drinking water from the local river. The river's getting the water from the precipitation. The pattern looks exactly the same as the stalagmite through time, the kind of the ups and downs, the curve. It's kind of a gradual decline, slight rise, a plateau, short drop, rise, fall again. And that allowed us to kind of compress and dilate the Liang Bua record to create a new chronology of the Hobbit bones.
Really?
Yeah. And it turns out that all of the, well, not all, but the vast majority of the Hobbit bones and probably majority of the stegodon bones all fall into this Goldilocks period. If we hadn't have had the tooth enamel, we might not really be able to say much other than if we just looked at the stalagmite record, we could have gone, well, they seem to have existed throughout this kind of wet, seasonal, dry period. But because we've got this tooth enamel record, which is it just lines up so beautifully with the stalagmite that you then can compress and dilate the Liang Bua record. And that just shunts all of the deposits into this Goldilocks, highly seasonal climate. And we think that the seasonality is important because that then allows for a kind of grassy conditions. So when you're very wet, it's just going to be forest. And when it's seasonally wet, dry, you're a bit more savanna-like. You've got a lot more grass. If you've then got your stegodon primarily eating grass, it's going to be a good time for the stegodon. They're going to be loving this Goldilocks period compared to the fully wet climate. And if you're a hobbit who's chasing and eating stegodon, you're also going to love this kind of Goldilocks climate period.
It's interesting. I didn't get that from my read through, which admittedly wasn't that detailed, but that's interesting that it's a Goldilocks zone of grasslands and forest mosaic that seems to have been ideal for these animals. Too wet, it's forested; too dry, it goes away. So, but the stegodon teeth, were they independently dated outside of being, what you said to the?
No, so it was all done stratigraphic position.
Okay,
And then there's a luminescence date at around 90,000. There's in the sediments, and I believe there's a date around 60,000 on a flowstone. That it's an archaeological sediment. They're difficult to date. You're beyond the limits of radiocarbon. So
yeah,
radiocarbon only gets you back 50, 60,000. So you find organic matter, you can't really date that. And so the chronology it's 2 points in a straight line, because that's what you can do, and that's fine. But then this allows us to refine that chronology because the match is so good.
okay. And the teeth are found in a deposit, layers of sediment with those two age control points. So you can say like these teeth are older because they're in a lower layer. These teeth are younger going up, but then you're able to then refine it by kind of matching the wiggles between the two.
Yeah.
Whoa. Okay. I was wondering that when I was reading the paper was if there were independent dates for those stegodon teeth. Were they able to do the teeth of the Hobbit, and were you able to look at that in terms of their isotopes to compare with your case?
I don't think there's an independent age on the Hobbit skeleton. It would not. That might need to be fact checked on that for sure. It's difficult to date bones in a tropical environment because bones are fairly porous material. You lose uranium fairly easily.
Okay.
Yeah,
Yeah.
it's a lot. Yeah, it's a lot easier to date things in a dry environment or in a cold environment, just because elements tend to stay put. And the same thing happens with, say, DNA, which is why we get great Denisovant DNA and we don't get any from the Hobbits. It's warm and it's wet. These things don't hang around.
That makes sense. They probably don't have many teeth of the Hobbit, maybe just a handful. So it really wouldn't have been able, even if you had them, I doubt they would have as many as the stegodon teeth. And most of the remains are like bits of bones. I think I have seen there is maybe a partial jawbone found Floresiensis, but yeah, I'm sure that the amount of teeth out there in the world from that species is very, very limited. So probably wouldn't have been that helpful if you had like one or two measurements with no dates. It's like, what can that, you can't really correlate that with your signal too much. Now, like I was saying, that's the Goldilocks phase. You put all these dates together, both the species. After the Goldilocks phase ends, there's little evidence. There are, let's say, few dates, if any, of the Hobbit and the Stegodon following the Goldilocks phase in the younger period.
Yes, exactly that. So following around 61,000 years ago, there is essentially no more Floresiensis remains, and there's a few Stegodon here and there. Right, then I think there is one Stegodon remain right up at the top of that unit just before a big ash layer at 50,000. So it's difficult to put precise ages on the disappearance, and that's okay. You don't ever want, we don't use the word extinction for that reason. We
Okay.
always use extirpation is probably a good way of putting it. But again, most people wouldn't necessarily know what the word extirpation is. So we just tend to use the word disappearance.
Oh, disappearance. And yet, for
Yeah.
those that are listening, extirpation is a local extinction of a
Local
species.
extinction. Yeah.
Yeah. And they could have been on another island, another place.
Yeah.
And things like that.
Yeah, that's the issue, is that they have never found Hobbit Homo floresiensis remains outside of Liangbua.
Mm.
We got an idea of their predecessor at and the stone tools of the predecessor, dating back 700,000 to 1.2 million years ago, I believe, on the island. So whatever was, and if that is the direct predecessor of the Hobbit, we don't know, but we know that there were hominins living on there for 1 million years.
Wow. Okay, now to build on the interest here, one idea with the extirpation of both of these species is that humans arrived maybe and killed them off or something. Your record, though, seems that it precedes the arrival of modern Homo sapiens on Flores. And so this suggests that climate, maybe alone, was driving the extirpation or the disappearance of these species, which I think is a pretty unique finding. And this is kind of bringing back to the introduction of this episode where, it seems as though the environment was determining the fate of these species more so than at least I give credit to. You know, do you have any thoughts on that, or do you agree with that finding still?
This is where the debate gets interesting in some ways. So yeah, there are no Homo sapiens remains in Liangbua until after this big, thick volcanic tuff unit. So there's no overlap of either bones or of tools.
When's that dated to?
So that will be less than 50,000. So the human remains will be
Sometime after younger than 50,000.
younger than 50,000. I want to say 45, but I couldn't. Again, would need to be fact checked. So that's the factual information. And then we get into kind of the speculation. One thing that we do is always we're trying to avoid climate determinism. Just because climate changed doesn't mean that you can contribute something that happened at the same time to it. And so we try to think of this in terms of ecological stresses. And you can stress a population before you make it go extinct. And so you have to kind of dissociate what might have killed the last Hobbit versus what caused their population to decline and for them to leave an area.
Mm.
So we know that from 61,000 years ago, it got drier and that the Stegodon and Hobbit not quite disappear from Liangbua, but essentially disappear. So they're leaving the area. And so you have to then piece together a story of what might have happened and why that is. And so the local river, the Weirukang River, it's not particularly large and it can dry up during particularly dry years, during the summer, during not the early summer, the end of the dry season. And so if you have a drier climate, there's the possibility that you lose the river. And we know because of the oxygen isotopes of the teeth enamel of the Stegodon that they were drinking from the river because they match precipitation. If they were drinking from puddles that had a lot of evaporation, we'd be able to tell. So we're pretty sure that they're drinking from the river. So our hypothesis, therefore, is that the river is drying up in this drier climate. The Stegodon are forced, presumably, to migrate. They're not going to hang around and just die in place. And if they're migrating out because of this climate stress, chances are if your prey's moving, you're just going to follow them to a more reliable source of water, which presumably would be downstream. And therefore, you can start getting into really interesting ideas that if we know that we've got humans, modern humans, Homo sapiens, traversing through Indonesia at this time, as 60,000 years, the kind of is a generally accepted date of arrival in Australasia. So, they're potentially they're definitely in and around Sulawesi, tens of thousands of years before that. They're definitely in Southeast Asia, tens of thousands of years before that. So you have to assume that they could well have been passing through Flores and probably via coastal routes. So even if you didn't have Homo sapiens traveling up to this kind of remote mountain hideaway where the hobbits were living, if the hobbits were then forced down to the coast, following the Stegodon, who are searching for more reliable water. There is a chance that they interacted with modern humans, and modern humans might have been the ultimate cause of the disappearance of the Hobbit. But that is getting way into the speculation. We know that they were being stressed by climate. We know they probably migrated out of that home area because of climate. And we don't ever see them in any record after that point. And there is also the volcanic tuff. You've got this giant layer of ash at 50,000 years ago. The island is volcanic. You know, we're only 10 kilometers away from the nearest volcano. You drive along the road and there are plenty of just ash quarries on the side of the road where people are mining the ash for aggregate and to make concrete. And so maybe the volcano was the thing that killed off the Hobbit at 50,000 years ago. Maybe it was humans sometime in that 10,000 years before, through disease, through competition, through predation. We don't know. We might never know.
Mm-hmm.
But what we can say is that it's clear that the Hobbits were doing well when the climate was highly seasonal, and then they disappear from their home when the climate dries up. So we've definitely got an ecological stress. As for what the causes is.
Do you see evidence for bottlenecks of modern Homo sapiens or other species at that tephra layer, like in Asia, that you're aware of?
No, I think it would be a step too far to try and... It's a volcanic island. There are volcanoes right there. I don't think there's a need to try and invoke some super volcano somewhere else potentially in Indonesia or elsewhere in the world that blanketed the entire region in ash and caused, utter devastation when, there are plenty of volcanoes. Yeah, there's no need to invoke a V7 or 8 eruption when a 6 might have done it.
Okay. Because, you hear about this story. I just looked it up here. You hear about the bottleneck in modern Homo sapiens, like in the mitochondria. Yeah, in the mitochondrial eve. And I just looked it up, but that's dated to 150,000 to 200,000 years ago.
Okay, and there is there is a bottleneck there. There was a bottleneck at 70,000 as well from the Toba super eruption.
Okay.
At least there was in the early 2000s. I do not know whether that still stands up.
20 years later. That's still before our Goldilocks. So there were still fossils even after this Toba eruption, including the dated Hobbit fossils.
Yes. So Toba is... Toba 74.
Oh, 74.
74. We believe we might have a volcanic eruption on Flores around 68 as well. That seems pretty significant. We see it in the carbon isotopes. There's just something which is going on there that's a bit unusual, but it's the big unit of tuff in the Liang Bua sequences at 50,000. So far, they're definitely unrelated to, say, Toba. And, why invoke something big when something small and local will do?
I think I've covered most of the stuff I wanted to talk with you about the study specifically. I think it's very interesting that maybe climate had something to do with the, evolution of our close ancestors in Southeast Asia. You did field work in Flores, right?
Yeah.
Many times. And how long were you there?
So the team were there 4 or 5 times, I believe, 2006, 7, 9, and 11. Then possibly 2005 as well. Might have been the year they discovered the cave.
I think that was 2003. I checked that before our interview here.
The Hobbit is discovered in 2003, published 2004. Okay. Liang Luar was shown to go on. Kind of our team went through Liang Luar in that time, 2005 or 2006. And there were subsequent field trips, 06, 07, 09, 11.
Cool.
Yeah, it's an amazing place to do field work. It's very remote. Kind of, it's hot, it's humid. Caves in the tropics are at mean annual air temperature, so about 28 degrees. They are at 100% humidity. And you start the day by wading through neck-deep water. So you're soaking wet from, minute 5 of your working day
Oh my God.
and you stay soaking wet because there's no evaporation until you get back outside at the end of the working day. It's tough, but it's so much fun. It's a great place to do field work.
That's classic type 2 fun, where
Yeah.
yeah, when you're doing it, you're like, what is going on? But when you look back on those memories, you're like, wow, what an experience. That was like, something a lot of people don't get to do. A lot of people don't get to see, most of the world never gets to do or see. So the reason I'm
Yeah, it's
curious,
exciting. There's only what, 15 people who have been inside that cave, all on our team. So
wow.
various over the course of the 5 field trips, I say around 15 different individuals.
So the reason I'm curious about if you've done field work there, because I really now want to get into some crazy speculation now that I have you on the hot seat. And you can say you have no opinion as well. Now, in my early episodes, I brought on Greg Forth. He's an anthropologist, and you may be aware of him. Or do you know who he is?
I
Gregory
do. I've
Forth?
read his book.
Okay,
Yeah.
awesome. I read his book too. This is perfect. Now, when you were out there, so Greg Forth, the book is called Between Ape and Human, and he is an anthropologist. He's an academic. He can speak Indonesian with the locals. He's not speaking through a translator. He doesn't speak some of the indigenous dialects, but he can speak with the local people. And he claims in his book that local people believe, and I have him on record on my channel, he believes them as well, that they say that they, at least in the 20th century, have encountered hobbits, that their description matches very closely to what the fossil remains suggest. And the stories that he collected about this hobbit, and they called it Ibu Gogo, they precede.
Depends. Yeah.
Okay, depends, but they
It
precede the
depends on
actual.
where you are on the island. So
All right.
Ibugogo is, I believe, the name given around that part. I believe that name isn't used by the actual area because Greg's field area is the other end of Flores. And so he's actually not, it's not the Ibugogo myth he's directly collecting information on. It's, but yeah.
But anyway, the stories he collected were also before 2003. So he had these stories of these small bipedal people living in the mountains of Flores, and then they find the skeleton. It's remarkable that it pretty closely matches the description he had. So I want to put you on the hot seat and see, first of all, did you hear any stories about these mountain people from local people while you were there? And do you have any opinions on Greg's story? And do you think it's a possibility that these hobbits maybe existed up until the 20th century?
So we didn't hear any stories, unfortunately, direct from the locals about that. You can't not go on fieldwork in Flores and speculate.
Okay.
It's just the kind of thing that happens when you're talking about hobbits and the environment and just, some of the relative wilderness and the density of parts of the jungle out there. There are 2 different sides to me on this. The scientist side says it's a nice idea. There's no proof, until it happens, you can't, it's kind of, there needs to be a rational scientific process that I'm not going to speculate whether or not it does or doesn't exist. We have no evidence for it currently existing, really, no scientific evidence. So I'd err more on the side that it doesn't. I also worry about what modern humans would do if it did exist. It would be brilliant, and then the aftermath would be terrible for the hobbits, unless it was phenomenally well managed. But as taking off the scientist hat, wouldn't it be great? Wouldn't it be fun if it was true? I think the book's really good. I think it's a great argument. Part of me does want it to be true, but the other part of me says probably not, and probably a good thing if it's not. Having said that, the idea is sound. I've been working in I've been working in Madagascar as well as Indonesia. And so there, the primary predator on the island is the fossa. It's a bit like a mongoose, bit like a cat, but neither. And we know of the current modern fossa that exists. Cryptoprocta is the Latin name, Cryptoprocta ferox. And we know from the fossil record that there was a slightly larger, potentially extinct version. And then I'm working on a paper at the moment where we have a leg bone of a potentially even larger Cryptoprocta species. I don't think in the paper we actually go as far as to say it's another species. We don't name the species, but we say because it's not enough of the anatomy. But essentially, it therefore seems like there's potentially 3 Cryptoprocta species. And when you talk to the locals, they have in there about what they think about the Cryptoprocta is they kind of recognize that there are 3 species of Cryptoprocta. The grey one, the black one, and the red one. And so, there's only 1 species alive today, but the modern folklore suggests that there's 3. The paleoclimate record, the paleoanthropology record and the archaeological record is starting to suggest, there's potentially 3 out there. So, it is, if you can do that with a primary predator in Madagascar, could you also do that with a hominin in Indonesia? And so and this is where the next layer of that story is that there is a PhD student, I believe, who has his own eyewitness first-hand account of saying, I think I might have heard one and possibly saw one when I was camping out in Madagascar, one of the larger Cryptoproctus that the locals say exist out in the forest. But then you're into, do you believe the eyewitness account of a white PhD student more than you believe the eyewitness accounts of the locals? And that just, you're wandering into cans of worms and speculation. And it's difficult to say anything for sure about kind of discovering these species that exist in folklore and in not necessarily even folklore. Folklore's probably not the right term. Just some kind of collective community memory.
That's interesting.
Lots of issues to unpack. It's a fascinating kind of discussion over a pint, but the scientist says, no, the Hobbit doesn't exist anymore.
Without like hard physical dated evidence, it's hard to, as a scientist, to say it exists. But you also don't want to discount these oral stories, or like you call it, a collective memory, because Madagascar has them. It seems like Flores has them. Native Americans have stories of megafauna in their oral histories that match pretty closely. I think even with the ground sloth or something like this in the southeast U.S. And that thing went extinct 10,000 years ago. And I guess the dates for Flores for the Hobbit are older than that, but I don't rule it out. And it's an interesting intersection where the oral histories of people living in the areas might intersect with science. But I think, the oral histories stand alone, but if the scientists can objectively hear them, interpret them, and, just place them in the record so that maybe one day evidence will emerge and correspond with these oral histories and maybe even complement them rather than just totally discounting them and pretending like they don't exist. And then if we find the fossil, it's like, oh, they didn't know about it. That's the part I think is interesting, is like Greg is setting the seeds. He's like, listen, there are so many accounts that I believe, and we have to at least have this in a book so that, if the evidence does emerge one day, maybe it'll help us out with interpreting it and learning about it. And we also have to remember the absence of evidence is not evidence of anything. So there's the absence of Hobbit fossils from 50,000 years up until, it sounds crazy, but up until the 20th century is not evidence that there's nothing there. It's just there's no evidence. That's the only evidence. It's the lack of evidence. So those things are all things that scientists need to keep in mind. And I think anthropologists, archaeologists, and geologists are learning that some of these histories are important for us to interpret our data. And they're becoming more and more relevant, I think. And that's all that the part that's interesting to me. And then the non-scientist part, like you said, is it would be so cool if you could see a real descendant of the Homo floresiensis, a two-legged, member of our like genus, and it exists. And like you said, then the implications, if they knew they were in this mountain, in the island, it would probably destroy them because people would come from all over to see it. It's on the order of like seeing an alien or like finding out like, something exists that we thought was extinct or never existed forever. And I mean, I didn't even think about that, but yeah, I think that would lead to their demise if they found there's some kind of refuge population somewhere up there. It would be hard for the government to contain it. How would you maintain it? Because even today, with these so-called uncontacted tribes in South America, they're having so much difficulty keeping them free of diseases and free of human modern influence, and they're under constant threat. And I just like imagine that with a small amount of population of these beings, let's call them in Flores. I mean, it would probably be their demise. I think you're right on that.
Yeah. Just sad.
It would be sad. It would be,
Human
or they would
nature.
end up in a zoo, or which would be even worse. I mean, to put, or something like that, a sanctuary where they wouldn't be allowed to leave or move around freely just to protect them, which is would also, yeah, like it would be sad as well. Well, Nick, this is, I love the conversation. Again, thank you for joining me on the channel. And for those that are watching, if you enjoyed the channel, please subscribe. It is free. Or like the video and leave us a comment below. Let us know what you think. All right, Nick. Well, talk to you again, hopefully. But until then, bye.
Thank you.